So look at this problem. X and Y are jointly Gaussian, zero mean random variables with variance sigma x squared, sigma y squared, and correlation rho. So they are jointly Gaussian random variables. Let's find out the covariance of x comma y. So this is in general, this is x minus mu x multiplied by y minus mu y. Here means are zero, so this is simply expected value of xy. Now the procedure I am going to show here is also, you can apply the same thing even if the means are not zeros. It just go through. So it's a fundamental, so by definition this is xy divided by the density function 2 pi sigma x sigma y 1 minus rho squared e to the power minus 3 terms 2 1 over 1 minus rho squared x squared over sigma x squared minus 2 rho xy over sigma x sigma y plus y squared over sigma y squared. Now to complete this, I'm going to complete the square on this on x, and then there will be some simplifications. So this is xy, so the constants are as before, sigma x, sigma y, square root of 1 minus rho squared, e to the power minus 1 over 2, 1 minus rho squared. So I'm going to complete the square here. So this is x minus sigma x minus rho y over sigma y the whole squared. And I'm going to add up the square of this term, subtract it outside from here. So that will be, so the terms on y would be, so I'm going to, so the last term here is rho squared y squared. So that should be taken out. It will be minus rho squared y squared over sigma y squared. So there is only 1 here. So the next term is going to be 1 minus rho squared over y squared over sigma y squared. So I'm going to simplify this, and notice that this and this would cancel. So I can write this whole thing now as minus infinity to plus infinity. And I see that this I'm going to write it by pulling the sigma x outside. So this would be xy over 2 pi sigma x sigma y square root of 1 minus rho squared. And here this would be 1 over 2 1 minus rho squared sigma x squared. Sigma x squared I'm pulling outside. So this becomes x minus rho sigma x over sigma y whole squared multiplied by e to the power minus. Notice that this cancels out. So this simply becomes y squared over 2 sigma y squared. And dx dy, of course. So I can split this integral into two integrals now. So notice that the y integral, I'm going to leave it here. So y over square, I'm going to split the constants also as sigma y squared e to the power minus y squared over 2 sigma y squared d, and where is y here? So let me complete this one also. So this is x, and here I have, so let me call this whole thing to be a. So if I write this as a minus plus a, then you have e to the power minus 1 over 2 sigma x squared multiplied by 1 minus rho squared And here in the numerator you have x minus a the whole square. Notice that this answer is very easy because x minus a multiplied by this density function is so divided by, let me take care of the constant, 2 pi sigma x squared multiplied by 1 minus rho squared. So this is a random variable x with variance sigma x squared multiplied by 1 minus rho squared and mean equal to a. So x minus a multiplied by the density function is 0. The second term is plus a multiplied by the density function. That's 1. So the answer is a. But a is, we just substituted for rho sigma x sigma y y. So I'm going to substitute that into the next page. So expected value of xy is integral rho sigma x sigma y y multiplied by another y, so y squared 1 over 2 pi sigma y squared e raised to minus y squared over 2 sigma y squared. But this is the definition for the zero mean variance, a zero mean Gaussian random variable with variance sigma y squared. So if I pull this constant outside, rho sigma x over sigma y multiplied by y squared over y squared over 2 sigma y squared. This is simply sigma y squared. Sigma y cancels and you get rho sigma x sigma y, a classic result. Also, this is also true if you for non-zero mean. So what's interesting is how do you do this? So I'm going to do this the next